individually hybrid bond those to a base wafer. So if you can think about it, one of the big issues with wafer-to-wafer bonding is what is the yield, or how many good chips are there on each wafer. If either one of the wafers is not a very high yield, if there's a lot of bad chips, then you're going to be essentially aligning one wafer that has some bad chips with another wafer that has good chips in the same position, so you're wasting good chips. So that's the downside, and that's why people are not adopting yet, but will be soon, chip-to-wafer hybrid bonding. Another style of package, advanced package, is something we call package on package. So you don't have to just solder the package, a package, to a printed circuit board. You can solder it to the laminate substrate of another package. And in fact, if you were to open up your cell phone and look at the application processor, they're almost all built in this fashion, with a bottom part of the package holds a processor and the upper part of the package holds memory chips. And these have just gotten a little more complicated over time, but the concept is the same: memory package on top and logic package on the bottom. And again, maybe a little more detail here again. So the memory chips are kind of in a standard package, standard wire bond package up on top. And then down at the bottom is a flip chip with copper pillar bumps attached to the lower substrate. And this has evolved now to package on package devices that include the lower package being a fan-out wafer-level package. So if you recall, the fan-out wafer-level package is essentially chips that are placed on a carrier and molded around, and can include these things that we call the TMVs, or through mold vias. So it's kind of another way to interconnect these, and the advantage is it's denser than the previous ways that package on packages were made. So Apple in particular relies on this type of packaging, the fan-out wafer-level package on the bottom with the DRAM on top for all their cell phones. So system in package, the concept is, pretty straightforward. You put more than one chip in a package, and other things as needed. Other things could be surface mount components or filters or optical components, whatever, to try and create that functional block at the package level rather than at the chip level. So this started in 1998. Where I was at Amcor, we were looking at this. Other people were looking at it, Georgia Tech in particular. And we recognized the difficulties with system on chip. High cost, complexity, slow time to market, and chips at what we call the reticle size limit. So the reticle size is essentially the maximum mass size that you have in the wafer fab, and it's a major limiting factor. It's about 25 millimeters on a side back then. And the SoC packaging was very difficult too. I had a group at Amcor where we were packaging the state-of-the-art SoC chips and flip chip packages, and we hadn't perfected the substrate technology yet or the assembly technology. It was very difficult. And so we started pushing this concept of, you don't have to integrate everything on the chip. Let's integrate it in the package. And we purposely came up with the term system in package as a contrast to system on chip. And this was actually the original SIP presentation that I put together in 1998, but it's still kind of pertinent today. It's just, and maybe even more pertinent today because, and we'll talk about this a little bit later, when we talk about things like chiplets and heterogeneous integration, the concept is kind of the same. So the big concept, again, use the package as a source for integration rather than just the semiconductor chip itself. And this one is kind of crazy, but I liked it because it's so crazy. People thought you could do everything at the package level, and I'm not sure that's the case. But a lot of things can be integrated at the package level. So why system in package? This concept, again, of heterogeneous integration. So different chip FAD nodes, different chip technologies can be put in the same package. The space saving and densification, which is always a driving factor. A thinner package. You can include parts that are not IC parts. We can include more IC area, more total IC area than you can include in one system on chip because it's, again, reticle constrained. And it's the ease of end customer integration. The more you can create the function at the package that's all inclusive or sub-function, the less that the end customer has to do on their design. Lowers the system board cost sometimes because the complexity of the wiring and routing is within the package, not at the system board. And typically lower chip cost because the chips can be optimized, the wafer fab process optimized just for one type of chip. Faster time to market. It's typically easier to integrate at the package level than it is at the chip level from a design aspect. Lower supply chain risk. There's only so many fabs that can make highly complex system on chips. And you can easily change the product. So this is just some examples of the kind of densification you can get. So you can see various examples here of an original design that was converted to a system in package and the type of space savings that you get on the order of 80 to 90% space savings. Another example here of how solid state drives for some companies have changed from board kind of integration to a package kind of integration. This is, excuse me, this is more of the same example. And you can see there a lot going on in that package, stacked chips and surface mount passive devices, etc. And importantly, the ability to include non-integrated circuit parts. So SMT passives is a common thing, but other things, like I've shown before, we saw some examples with antennas in the package, but you can have filters or duplexers or switches and RF parts, connectors, flex cables. Here's an example where the package is encased in a card. So our memory cards, SSD cards, for example, all have a little package inside them. And, I think it's maybe overlooked because people oftentimes kind of focus on the mechanical side of things and the space reduction. But a big advantage to this kind of thinking is that you can make this part easier to integrate at the next level. So if you have fully designed a functional part or a sub-function into a package that's fully tested, then your end customer can more easily implement that. And so, for example, in some of these RF parts, the reason there's all those passives in there and filters, et cetera, is that they're doing all the required matching and tuning, electrical matching and tuning to make the RF circuit work is done inside the package. So the customer can put a known good part on their board and it will work. So this is, again, just another example, but you can see here what's going on. A lot of integration in some of these front-end modules. So you see on the right there, 27 chips and 46 SMT passives all in one package. And again, looking at this in cross-section, you start to become pretty complex. The substrate is complex. You know, it's a coreless substrate. Looks like it's got about 12 layers maybe. It's got shielding on the package, flip chip die, and switch die in there, and surface mounting. So very tuned for the application. So this is kind of a computer in a package, if you will. Essentially, all the functions, or most of the functions in a computer, can be put in a single package. There's more detail on that same system. Slightly different application, but again, essentially a computer in a package from a different company this time. And we can see their package on package format, so memory on top and the processor below. This is another picture of a RF part. FEM stands for front end module, so this would be like, you know, where the signals come in to the device, and our first recepted from the antenna into the chain for a wireless part. I think the image on the right is kind of interesting. So a lot of times we look at x-rays before we start opening up the packages to see what's inside. And silicon is transparent to x-ray. So if you look at the middle picture, you see the bumps of two chips, but nothing else. And then if you look at the 3D x-ray on the right, you're seeing the same thing. The silicon chip is transparent, which actually really can be helpful if you're doing a detailed investigation of the inside of the package without having to tear it apart. So another advanced package that's become quite popular is this fan-out wafer-level package. So the key here is that the molding material, the encapsulant, is not only used to encapsulate and protect the chip, but it's used as a basis for the wiring layers that are built up on top. So the RDL is built up not only over the chip itself, but to the extended mold compound outside of the chip area. So it's difficult to see there, but on the bottom, what happens is that the wafer is cut into chips, diced, and then the chips are put on a temporary carrier but spaced apart and molded over. And so that's how we get the mold outside the edges of the chip. And that mold compound is ground down to expose the bond pads or bumps on the chip. And then we put RDL on it and dice up that molded wafer to get the individual packages. So an example of one of these parts is happens to be a multi-chip part. There's two chips in this fan-out wafer-level package. But in the lower left, what you're seeing is the RDL traces built up on top of the mold compound and going over the edges of the chips. Excuse me. This is just some detail. You can do, for a fan-out wafer-level package, you can either do the process that I just described, which is called chips first. So the chips go on the carrier or molded, and then we put the RDL on. Or you can do what we call chips last. You build the RDL on a carrier, and then you attach the chips to that RDL, and then mold over it. And both are practiced, but chips first is more common. So I think I mentioned many of the all the Apple application processors since maybe the iPhone 7 use a fan-out wafer-level package to interconnect and encapsulate the processor chip, and then on top of that is mounted the memory chips. And this is just a cross-section close-up of what the bump looks like on some of these Apple chips that go into the fan-out. This is talking about the initial wafer prep, so putting some bumps on the chip, dicing the chips, and then this is the process flow where the through mold vias are first plated up. They're kind of that blue, tall structures, and then the chip is placed and molded over, and the RDL built up over it, and then finally solder balls are put on. So you can see here kind of what some of this interconnect looks like at this level. It's a lot, in this case, the process is different of how the dielectric is applied versus at a wafer fab. So you kind of see a waviness to both the dielectric layers and interconnect layers. And this is a slide I showed before, but they're smartly using that level of bump, not only as a bump interconnect, but also as a power distribution network wiring. And they're segmenting that into different voltage areas depending on what parts of the chip they're supplying power to. And you can take that fan-out concept and apply it in many different ways and extend it. And so people are doing that, going from one chip to multi-chips in a package to including surface mount parts in the package, multiple layers both on the front side and the back side of the package, etc. So we talked about bridges as a component to packaging, and so when you include those bridges or interposers in the package, that's a form of advanced packaging. So as I said, 2.5D packages are used for essentially all the high performance packages that go into data centers and AI applications today. And bridges are just starting to kind of enter that same realm. Again, the bridges are smaller. They have the same local interconnect density, but since they're smaller, they're lower cost than a full silicon interposer. So you'll find them in these kind of high performance computing applications. Again, where that memory stack, in this case the HBM memory stack, is directly adjacent to the processor, and then the bridge connects the two. So more examples of the same, what some of these things look like. You can see in the middle picture the HBM are kind of blue color and the GPU is in the center, but bringing those memory chips as close as possible to the processor. More examples, the same example actually, showing more detail of the interconnect. So the copper pillar bumps connect the GPU to the interposer, and then you see the interposer itself has TSVs through it, so it can connect from the chips above it to the substrate below. Essentially the same kind of thing, built a little differently. The process flow is different for this, but the result is the same. Trying to use these bridge chips to make a very high-speed interconnection between the chips above them. And in this case, it's a combination. It's a bridge, and then there's RDL layers also applied above the bridge. So it's kind of goes back to the concept of using your building blocks and your knowledge of the materials and the processes. How can you combine these things in interesting ways to achieve what you want to achieve? So this one just spells out a little bit what the process flow looks like. Essentially making an organic interposer with an embedded bridge in it in the first step. So there's no active silicon in A, B, or C. And then in D, you attach the active or functional chips to that interposer you've created. And then that in turn gets placed on a larger package substrate. So lots of layers of packaging going on here. There's other kinds of packages that are specific to the application. So in particular, MEMS devices, which are most often used as sensors, require specialized packaging. So for example, a pressure sensor needs access to the outside environment to sense pressure. So you have a package that necessarily needs a hole in it. So it requires specialized techniques. And here's some examples of some of these packages that have holes in them. Could be for a pressure sensor or for a microphone, as shown below. So MEMS is a whole nother area of semiconductor technology we haven't really talked about today, but MEMS again stands for micro electromechanical systems, but essentially things that move inside the chip and are used to sense acceleration or orientation or acoustic waves, etc. And then SAW and BAW filters, so these use also MEMS processing, and you'll see these throughout wireless phones. I'll step back just a minute and I guess talk about sort of the history. I'm not going to go through obviously every item on here, but it's a relatively young industry, Really semiconductors started in the late 50s, and so it's not even 100 years old, and we've made amazing progress in this industry. And packaging has been part of that progress. So kind of going through the early wire bond stages with very simple lead frame packages, but then getting more and more complex, first with flip chips, then with a change to laminate substrates, and then kind of a proliferation of very many different types of packages that we're in today, and a real focus on very high performance. And I would say, kind of the trajectory of packaging is maybe the same trajectory as at wafer fab level. What started out simple has become more and more complex over time, both in terms of structure, but also materials and processes. So this is just kind of showing a trend of over history and over time of the types of packages. So you can see that pink color was some of the original through-hole packages that I described, and then the surface mount area next to it. And then from there we went to the QFN lead frame packages and wire bond area packages and flip chip and some of the other more advanced technologies. But the old stuff never goes away, usually because it's very cheap. So again, by unit volume, still wire bond lead frame molded packages are the most common. And we've kind of made that transition from, or are about to make that transition from, a packaging area that was mostly kind of traditional and old style packages to advanced packages really taking over the market share. And this is another breakdown of the same thing, but with a little bit more detail on what type of advanced packages. So you can see there SIP and flip chip CSP and flip chip BGA. And then in the green, the 2.5D, 3D, that's really very high performance focus. So I'll try and talk a little bit about the trends, overall major trends maybe affecting packaging. So in the yellow on this chart, what I'm trying to highlight is some of these transitions. So, the original through-hole devices were redesigned to be able to be surface mounted as surface mount technology took off. And then surface mount, which was originally for peripheral parts, peripheral bond pads on packages, transitioned to area array packages, again for densification and higher I/O in a small space. And then we kind of got into this era where packages were designed very much for their application. And so I refer to that as application-specific packaging. So when I was at Amcor, we'd had customers come to us and say, we have a certain need. This type of device needs to go into this type of system. And we would design a custom package just for that application. And on the chart here is this thing, which I'll explain more in a minute, is what we call more than more. So Gordon Moore was one of the founders of Intel, and he wrote a famous paper where he said that integration of ICs, integrated circuits, would continue at a pace where density would double about every 2 years, and it would just go on forever. And for a long time, that's what happened. So for 20 years or more, the industry doubled the number of transistors on an integrated circuit chip, but not anymore. So we've kind of fallen off that trajectory. And it's been a problem for the industry to figure out, what do we do to react to this? How can we continue to densify, improve the functionality of our parts when we can't rely on this transistor doubling every 2 years? And so part of the answer to that is packaging. And packaging has become more and more important in the last 10 years because people realize that's another route. And we refer to that kind of thinking as more than more. So you can't just rely on the densification at the integrated circuit level. We have to do other things. I can't overestimate the influence that mobile phones had on the packaging industry. So, prior to that, we were packaging stuff that went into desktop computers or pretty big laptop computers or automotive or lots of places that weren't really space constrained. But when we got into the portable era, and especially the mobile phone era, everything started to change. And so the mobile phone manufacturers, of course, if you've ever seen the original Motorola mobile phone, it's about this big, and it weighed a few pounds, but people couldn't carry that around. So how do you shrink that? And how you shrink that is not just through silicon, it's primarily through packaging. And so how do you make these packages smaller and smaller? So here's an example. You can see in this phone. So this was a transition that was made as an example of a flash that was in the phone. This is an Intel flash packaged in we call it TSOP package. And then they transitioned into this micro BGA package that was thinner and significantly 80% smaller to go into the next generation phone. So, it's not just incremental little changes, not a 5% change. It's like some of these changes are like this, 80%, smaller is a huge change. So high performance, whatever you want to call it, high performance computing, HPC, or artificial intelligence, or 5G drives this, 6G is coming, smart devices, data centers, but essentially everything that's really high performance, meaning high computing power, high speed, high bandwidth, low latency, low power consumption if possible, more memory. So advanced packaging plays a critical role in all of this. And this is just, these areas are just, growing like crazy. If you watch the stock market and you watch NVIDIA, which is a major chip supplier into the AI space, I mean, their stock has just gone crazy over the last couple of years because the demand is insatiable. So this is what I'm talking about, Moore's Law, where there's doubling of transistors on every chip every 2 years, difficult to sustain, and the reason is a lot of different reasons, but at the fab level, there's lithography constraints. So lithography is a patterning process. So you've got to go to ever smaller wavelengths so you can print smaller lines and spaces and transistor contacts, etc. And the transistor design itself has become more complex. So we went from planar transistors to something called FinFETs, which is in high use today, and just now emerging gate-all-around transistors. But complexity is increasing over time, and primarily driven because we're getting to the atomic scale. The transistors are so small that it becomes almost impossible to shrink them further. The chip size, wanting to increase beyond what the reticle limit is. And some technologies don't scale. They don't scale well. So you see on the chart at the right, logic scales pretty well, but memory and analog don't scale. So it's difficult to reduce those and densify those over time. So this is just an example of this transition. We're actually going through this transition now, where transistors are being redesigned yet again to deal with leakage currents and things at the transistor level. So this idea that we went from a planar transistor to a FinFET where the gates are on 3 sides, and to now where the gate is all around that channel. And this is a chart showing when production will start. So this is just happening now. Samsung is already in production, and Intel and TSMC not yet. And on the left there is a kind of a picture of these gate-all-around transistors. So the little darker areas in the center of those stacks are the channels, and the material around it is the gate. Other things that are coming on the semiconductor side, backside power distribution. So everything we've talked about and all the images I've shown so far have been the power and the signals all coming from one side on the integrated circuits. And you can imagine, as the left diagram shows, if you're trying to drive high current or high power down through this stack of interconnects that may be 5, 10, 15 layers, that's not very efficient. So what people are looking at doing and will be doing in the near future is bringing the power from the backside and having all the signal routing on the other side. So these also, of course, have implications for packaging. This is just a different kind of diagram of that. What's interesting in some respects of this backside power implementation, we're using that grinding process again. So once you build the interconnects on the signal side, you grind the backside of the chip essentially very close to where the transistors are, where the implants are in the silicon substrate, so that you can make very short and very small diameter vias through the remaining silicon, and then you build up the backside power interconnect on that backside. But it ends up with the almost nothing left of the silicon that you started with. So the left is just kind of a depiction of what the process would look like as you go through. And then the right is a test part from Intel, where they're starting to demonstrate this. And that red line is the thickness of the transistor area, and everything else is interconnect. So I talked about Moore's Law, difficult to sustain. Part of it is the economics. So the cost per transistor keeps going up, and yield becomes an issue, especially on large chips with billions of transistors. And then for the lithography side, there's only one supplier of extreme UV systems, very short wavelength systems. So those systems cost $150 million each. And they're delivered in 40 shipping containers, and they're extremely complex. And it's crazy how they work. So the extreme UV light is created by blasting molten drops of tin with a laser in a vacuum and bouncing it off mirrors made by Zeiss, who say they're the flattest surfaces in the world. So the complexity of semiconductor fab, I would say, is an order of magnitude more complex than packaging. It's crazy. And there's only a few companies right now, Intel, TSMC, and Samsung, that really have the resources to make state-of-the-art logic fabs. And so TSMC's 2-nanometer fab is expected to cost $33 billion. We talked about this, so the scaling limits and by different types of devices are kind of running out of steam, but even for logic, it's slowing down the density over time. And we're at the reticle limit for some of these devices. So what do we do about that? We do integration at the package level, right? So we do what has various terms in the industry, system in package or heterogeneous integration, so that we aren't limited by this, and so that we can optimize each chip at its fab node for what it was intended for, and then the integration is at the package. So again, this term more than more, or heterogeneous integration, or system in package, this is all talking about the same kind of thing. You'll also hear the term chiplets. So rather than design a big, massive system on chip, those functions on that chip will be separated and into areas that we call chiplets. And then you recombine the chiplet at the package level to form that overall function. So it's really, again, advanced interconnects that help make this era possible. So 2D interconnects, the 3D interconnects that we've been talking about, the bridges, the interposers, RDL, that all plays in here. I guess the other thing, I may have mentioned it, I'm not sure, but there's definitely a blurring of lines between what is semiconductor packaging at the fab level versus what is semiconductor fabrication at the fab level versus what is packaging. A lot of the processes and equipment that we put in at Amcor when I was there you would find in a wafer fab. Now, we were doing the same kinds of sputtering and plasma etching and stuff that was done in a fab, but we were using it for packaging. But where that line is between packaging and semiconductor fab, it becomes more and more difficult to try and define. This is just an example. This is a part that went to production. It's in a supercomputer in the U.S. I think it's still the world's second fastest supercomputer. But again, the statistics here, right? So 47 active tiles, 5 different fab process nodes, 100 billion transistors, all in one package. So when you increase the number of transistors, you necessarily increase the number of signal lines that you need to access those transistors. And when you increase the number of signal lines, you're also necessitate an increase in the number of power and ground lines. So typically we have 2 or 3 times the power and ground connections as we have signal lines. So it's kind of a iterative effect. You know, you increase one, all the others increase. And so that has a large effect on the package, obviously, as the densification and number of transistors increases and the packaging becomes more and more complex to meet that density requirement. We've talked about a lot of this. This is just, I guess, a different diagram showing kind of the same stuff. But, you know, in this diagram, rather than talking about chips, we're talking about chiplets. So again, very smaller, functionalized ICs that can be combined at the package level. And in this case, we're seeing an interposer on one part of the package, and then a package substrate and a bridge. And in that interposer, there's also another bridge. I imagine that we will see real life parts like this in the very near future, where we're taking all those various building blocks to try and achieve the functional integration that needs to be. This again just is talking about mainly, you know, what is your substrate and what is the pitch or what is the density you can support, going from printed wiring boards to HDI substrates down into, well, they label it back on the line here, but that would be silicon interposer. And so the joining technology has to scale, obviously, with the pitch. So that transition from wire bond to flip chip to copper pillar flip chip to thermocompression bonding, micro bumps, and now hybrid bonding. With really hybrid bonding, maybe the only technology we can see today that's going to be able to integrate at these densities. This chart is essentially saying the same thing. Density is moving, and we need to react to that with hybrid bonding. This is essentially a similar chart talking about the pitch, line and space pitch, and I/O pitch, but they all move in concert, right? So if our interconnect pitch has to reduce and our line in space pitch has to reduce, or via pitch has to reduce. So making sure we have the technologies and processes to support that is all what it's about for packaging research anyways. I'm going to skip this one. So yeah, I'm not sure if there's anything new here, actually. One area I didn't really talk about yet, and this is the only slide I think I probably have on it. because it's not happening yet. This is kind of future looking, but you probably understand that for high-speed networks and long-distance networks for communication, oftentimes we use fiber optic cables, so non-electrical cables. So light travels faster than electricity does in a copper wire. So there's a desire to try and bring that kind of technology either onto the package substrate or integrated into the package. And people are working on that, but we're not there yet. So one of the interesting trends over the last 10, 15 years is that what used to be just the traditional wafer fabs have also turned into some of the packaging leaders. And that's because they have some of this technology, the dielectric application and interconnect capability, and certainly the lithography to be able to make very fine pitch and dense interconnects that the packaging houses didn't originally have. So you'll see that TSMC is, at least for Apple in particular, and maybe for NVIDIA, is a major packaging supplier now. And Intel wants to be. We'll see if they get there. And Samsung is kind of a little further behind. This is TSMC's roadmap. I don't think we have to go into this detail. And so what you see on the left are the foundries. It's very difficult to read probably in this on this chart, so sorry for that. But on the left are the three foundries, and on the right are something we call OSATs, outsourced assembly and test. So those would be independent companies that all they do is packaging. And you can see kind of where the technologies line up. And if you look, for example, at hybrid bonding, TSMC is there, Intel's there, Samsung not yet, and none of the OSATs. So the OSATs are actually a little bit behind today in terms of the most advanced packaging. Another thing I didn't talk about, but is future looking, is what is the appropriate substrate material, and we've talked about lead frames as very simplistic substrates. We talked about laminate substrates, both standard and HDI, silicon substrates, which are the most advanced today. But forward-looking, a lot of people are starting to look at glass as a nice substrate material. It has a lot of good properties. It has a CTE, or coefficient of thermal expansion, that's pretty close to silicon. It can be made very flat, so it's good for lithography. Has a very nice dielectric properties. So it's very possible that maybe in the next few years we'll start to see this emerge in some applications. I'm going to skip this one. So this is a prediction from one of the market assessment firms that's out there about what's going to happen in terms of acceptance of chiplets or heterogeneous integration or system in package into these various application areas. But primarily, if it's performance driven like server, they're going to adopt first. PCs will follow maybe. And then consumer and automotive, which generally aren't very high performance driven, will follow much after that and probably not adopt much because the cost is prohibitive for their needs. Turn a little bit to the markets and economics. So the global semiconductor market is huge. $500 billion, I guess, and growing at a decent pace, about 9% per year. And a lot of growth, in particular, on the right-hand chart, you're seeing where the highest growth is there at the bottom. So automotive electronics, wireless, and computing and data. And this is the same market but broken out by types of semiconductor devices. So you can see memory there at the bottom, and then analog, or logic, and then analog, and then processors and others. So I talked about this concept of application-specific processing. I didn't put this chart together. I found it somewhere. But on the left is kind of the end application, whether it's automotive or mobile or whatever. And on the right is the type of package, and in the middle is the device, whether it's a processor, an ASIC, or whatever. And it just becomes kind of like spaghetti. Everything becomes used for everything, right? So a package that gets developed for one thing might be used for another thing. So you end up having, many, many different specific types of packages. We saw something like this earlier. So this is the, by unit volume, what the IC packaging trend is. So it's just trying to point out that, even though, and including myself in this talk a lot about the most advanced packaging and the kind of most technically challenging. If you look at where most of the packages that are made today, what type are they? They're pretty simple. They're pretty simple wire bond, lead frame based plastic molded packages. And sometimes extremely simple. Sometimes they only have, less than 10 I/O on them. So when you say, what's the most important package, it depends on your definition. If it's by unit volume, the old school lead frame package is still the most important. If it's by advanced technology, then it's something else. We saw something like this a minute ago, but this is again kind of looking at what the adoption of chiplet type of packaging will be over time. So this is a list of packaging suppliers, companies like ASE or Amcor where I used to work. But then again, my comment that the traditional foundries, wafer foundries, are now playing a bigger and bigger role in packaging. So they're in the top 10 for sure. And not nearly as expensive as outfitting a new wafer fab, but packaging still requires a lot of, we call it CapEx or capital expenditure. So for equipment or new factories or whatever, so about $15 billion a year, or in 2022, about $15 billion. And you can see there some of the biggest spending is again at the foundries by Intel and TSMC. In terms of materials, I mentioned for a lot of high performance packages, the substrate may be 50-60% of the cost, and that's reflected here in this overall materials market. So you can see that laminate substrates is over half the market, followed by lead frames and bonding wire. Okay, I'll talk a little bit about testing. So sometimes in the industry we refer to ourselves as assembly and test companies. So a typical part of what we do is also test the devices once they're assembled. So I'll talk about that a little bit. And there's two types of tests that are typically done in a process flow. So there's usually a test at the wafer level. We call that probe test. So the wafer's still in a wafer format, and probes come down, and an electrical tester exercises the circuits on that wafer to a certain extent. But it's typically not a full functional test. You typically have to wait until the chip is fully packaged before you can do a full functional test. So We typically call that final test after assembly. So I'm talking here also about something called, KGD, or known good die. The problem with doing that probe test is it's not like I said, not a fully functional test. So sometimes you don't quite know if the die is good or bad. And the problem is if you're putting it in a package, especially if it's a package that has multiple chips, that can severely affect the package. If it turns out to be bad, then you've kind of wasted a package and all the other chips that were in the package because of one bad chip. Because generally the packages, once they're assembled, you can't rework them, you can't change them. So it's very important, especially in the chiplet era, to try and come up with better ways to test. So this whole idea of known good die, or trying to increase the testability of the chips while they're still in wafer format is really important. So, how do you do that? How do you address this known good die issue? So one option, choose a package so that you can test the chips before they're combined together. So for example, the POP or package on package that I showed before, like Apple uses, one of the reasons they have that secondary memory package soldered onto the top of the lower processor package is that the memory can be fully tested. It's in a package format. It can go through a final test. You can know with 100% certainty that everything is good before it gets committed to the final package. There's also things called wafer level test and burn-in. So as much as possible, you try and expand the test coverage at the wafer level, including, in many cases, there's things called self-test circuits that are designed in as part of the design of the chip. And during a test mode, you contact these circuits and they fire up and internally test a lot of things in the chip before it's out of the wafer level, and that helps. And then in some cases like HBM, so this memory stacks with a TSV between them, the designers really did a good job of thinking through what might be problems that would occur. So for instance, if one TSV is bad, you don't want to throw out the whole memory stack. So they did a good job of both anticipating how to test and find that defective TSV, but also have extra TSVs that can be brought into place, kind of like activating a fuse and cutting out one part of the circuit and using a different part. And that's what I was just talking about. I mentioned this before, but if you're doing hybrid bonding, wafer to wafer, this problem becomes very, very important, right? Because there's no way around it. If there's a bad chip on one wafer that lines up with a good chip on the other wafer, you're going to lose the good chip. So having high yield in these cases is critical. Just the density of the interconnects creates a physical problem. It makes them difficult to probe. So traditional probes that have been used in the past aren't really adequate for the current tight pitches of advanced packages. And there's lots of considerations when it comes to probing. You don't want to damage the bumps or bond pads on the chip, et cetera. Talking about more kinds of things like this, damage on bumps, et cetera. So what people are starting to use are advanced probe cards. This thing that holds all the probe is called a probe card. And you see all kinds of solutions now. Probably one of the more advanced is from this company called Form Factor, where they use MEMS technology to actually shape these probes at very, very dense pitches so they can contact the most advanced chips. But in general, the test industry has been able to keep up with the interconnect densification. It becomes much easier at the package level, so this is the final test that I referred to. We call it final test after assembly. So in this case, the package has already now distributed the I/O to a wider pitch that's suitable for surface mounting. And that means it's also much easier to contact in kind of standard sockets and test handlers. I will go through this part fairly fast because it's kind of deep in terms of the theory and maybe some of the thoughts. But essentially, you can think of the package as an integral part of the circuit. Right? So there's a circuit on the chip itself, but the interconnect of the package, and from there the interconnect on the printed circuit board that interconnects all the components is all part of a circuit. And so electrical performance plays into how those circuits are designed physically. How many power and ground do you have per signal, and what's the arrangement, physical arrangement? Because those traces, when they're carrying a signal, will interact with each other through capacitive coupling or inductive coupling or other electromagnetic effects. And so we take all that into account in our packaging. One of the most basic concepts, though, for performance is just make the interconnect as short as possible. So I've talked about this a few times where, bringing the chips into the package and bringing them as close together as possible ultimately drives short interconnects. Stacking them with TSVs makes short interconnects. So shorter is almost always better. I'm going to skip some of this. This is kind of more of what I was just talking about. So oftentimes a package that was originally designed for a wire bond interconnect will be converted to a flip chip interconnect purely for performance reasons, that flip chips bumps are a lot shorter than wire bonds. I guess just as an example, well, I think I'm not sure I want to get into this level of detail, sorry. So, equivalently to electrical performance, thermal performance is critical. So some of the higher performance chips that go into data centers now, each chip dissipates maybe 300, 400 watts, some of them going up to 700 watts. That's a lot of power. And trying to get that out of a system that has, multiples of these on a rack in a server is a real problem. So we talk about kind of equivalently to electrical resistance, which is a concept most people understand. We talk about something called thermal resistance, but it's essentially, how difficult is it to transfer heat from one place to another place. And we talk about it both in terms of inside the package or external to the package, so from the package to the environment. Talking here about the different heat transfer modes, just kind of the physics of heat transfer, but for packaging, almost always it's conduction is the most efficient way, and then convection heat transfer, which is essentially blowing air on something, is the next most efficient way to get heat out. So because conduction is the most efficient, you'll see us design into packages various ways that we can directly conduct heat. So it might be things like implementing what we call thermal vias in the substrate, and they can be filled up with conductive material, or we bring that pad out, like on a QFN on the left, to the bottom of the package, so it can be directly soldered to the printed circuit board, and the heat conducted to the board, things like that. And so we look at all these things to try and optimize the best way to cool the package. So I mentioned that, you know, in today's data centers, maybe the highest performance chips are at the 300, 400 watt range, some maybe up to 700 watts. You know, NVIDIA's Blackwell, which isn't quite out yet, but will be soon, they're predicting 1,200 watts on that chip. And when you get to that level of power at the system level, you're automatically having to go to liquid cooling. So if you see an advanced supercomputer or advanced data center rack, they're all liquid cooled now. So the package will sit on a board, and then a liquid cooled cold plate will sit on top of the package lid. I'm going to skip this one. Skip that one. So oftentimes with packaging, you know, we're working with the next level of designer and customer, and they're telling us, you know, what the application is, so we can understand it, so that we can help engineer what the heat flow path needs to be, whether it's out of the top of the package or the bottom of the package. So, you know, this is all at the kind of next level of packaging, but this is what our package needs to connect to sometimes. So you see a variety of things here. On the left is kind of a big heat sink with a fan in it, and it sits on top of the package. And on the right is one that's liquid cooled, but same kind of thing. So these are just different options for a high-performance laminate-based package. You can put a little preformed lid on it, or a more complex lid is in the upper right, or in some cases, no lid at all. And in that case, the next level of thermal cooling will just attach to the backside of the chip. And this is what it starts to look at some of the next level. So there's a, you know, a rack system with liquid cooling in it. Again, very common for the higher performance servers. So basically, going from no cooling, and many devices, probably most of the devices that are packaged today don't require any kind of cooling because they're very low power. But as the power at the package level increases, then you have to worry about the subsequent cooling all the way up to the liquid cooling. Skip this one. Sorry. So let me talk a little bit about the package design process and what goes into that. So for the vast majority of packages, they're just standard off-the-shelf packages. You know, somebody comes to an assembly house and says, you know, I have a device and it doesn't dissipate much power and it's about, you know, 40 leads, and we say, okay, you can put it in a 40 lead quad flat pack, no problem, standard parts, very cheap, and everybody's happy. But oftentimes, you know, the customer will come with a very complex design, and we really, even though we're just doing the packaging, we get very involved in the design of the final part. And so these are some of the kinds of things that we might look at. So a customer, in this example, is showing some kind of a wearable wireless device. And so they have a microcontroller and an ASIC and a FPGA and power management IC and a charger. And they have connectivity, wireless connectivity, and memory and other things going on, LED display. And so the packages have to respond to those kinds of lists, and we have to understand them. So we have lots of constraints, and not just, you know, the physical constraints, but also constraints on the overall function. So oftentimes for advanced packages, we're trading simulation models with our customers. So they give us a simulation model of how their IC functions, and we take that and we put it in a simulation model of how the package functions, so that we can make sure that what we call critical nets or critical traces are properly designed to meet the high performance requirements. So we try and take all these things into account when we design. This is more about the typical flow that we go through. So review the technical requirements. There may be some component selections. And then we start looking at component placement and routing of the substrates, do a prototype build, maybe even a test board build. Typically the customer would do that. And then verify the performance and do simulations and testing to make sure it all works. So I see we have a key site call out here. So again, a lot of advanced design CAD tools go into packaging. Not as advanced as wafer design, but pretty advanced. And similarly, along with that, a lot of advanced simulation tools and electrical modeling tools and thermal tools, and also reliability, stress analysis. I won't go through all this detail. But I mean, to give you an example, so one of my previous jobs was I ran the SIP group at Amcor, but some of the people I hired were, you know, PhD guys that knew a lot about electrical simulation and modeling, and they usually came out of the IC world and then transitioned to packaging because we didn't really have those type of people. So I mentioned we use these CAD tools and finite element model tools for mechanical simulation also. The mechanical side is more around whether the part is going to meet the reliability objectives and if we're getting too much stress. Talk about costs in general terms. So again, substrate materials make up the largest percentage of the package cost, and it kind of goes in that order, lead frame being the cheapest, then laminate, ceramic, and then silicon with thin film. And the laminate costs, you know, go by complexity. So if it's a simple, non-dense kind of standard substrate, that's no problem. If it's HDI, it becomes more expensive, and the number of layers, number of vias drives that cost higher. Wire bonding is the cheapest chip interconnect, followed by solder flip chip, and then copper pillar bump, and then RDL, and then hybrid bonding, with TSV being the most expensive. And kind of in the same order as the material cost, wire bond is the cheapest assembly, followed by flip chip, and then TSV. And test can be quite a lot of the cost of a final package too. I don't really address it much in the previous comments, but you know, in a final package cost that includes test could be as much as 20 or 30% of the cost. I think we could skip that. So it's always critical to consider reliability. So reliability is essentially, is that part you've designed able to continue to function all through the lifetime of the product that it's going into? And so we test for that. In the packaging world, typically the weakest link is something we call solder joint reliability, or SJR. So that connection between the package and the system board that it's mounted on. And that's highly driven by something we call CTE, the coefficient of thermal expansion. So silicon expands at a rate of about 3.6 parts per million per degree C, but a printed circuit board expands at about 20 parts per million per degree C. And you have to make up for this difference and design for it. And the problem is, you know, you generally join things together at a higher temperature, everything's expanded and in the same position, but when you cool it down, if the printed circuit board contracts much faster than the silicon, then the part warps, for one thing, but it also puts a lot of stress on the silicon, or any interconnection between the silicon and that substrate. So we have models that we use to try and predict the stress on the joints and the lifetime of the joints. But I guess generally what we can say is that you know, for flip chip parts, you have to use an underfill. That's kind of mandatory in almost all cases. And then we do whatever we have to try and balance the stresses both inside the package and between the package and the printed circuit board. And if we don't, we get this. So this is a flip chip crack. So this is between a chip and the package substrate. And this is a crack between a chip scale package and a printed circuit board. So I'll just go back for a second. It's the same kind of morphology. So in essence, it's all about the same thing. It's controlling that stress on those solder joints so you don't get these kinds of cracks. And those cracks will start at a region of high stress, and then they propagate across the solder joint until the solder joint fails. Okay. I'm going to skip some of this detail. And we can look at this with computer modeling. So we always do this. It doesn't always tell us exactly what's going to happen, but it at least generally tells us areas that are of high stress and that we should be concerned about and look at. There's other package reliability issues. One of them is called electromigration. So that's when metal atoms will move under the force of a high current density. So it's kind of the current is carrying the atoms and moving them around, and can lead to failure. And there's lots of studies that have been done on this, and you start to see these kinds of voids that form due to electromigration. These are in solder flip chip joints, and kind of more looks at that. But one of the good things is that copper pillar bumps, not only do they help us reduce the pitch of the bumps and increase the density, but they're also much more resistant to electromigration damage. I'll skip this one. In general, to address this issue of solder joint reliability, one of the things that can be done is to try and sort of support the solder joint. So you see here that molding all around some taller copper posts before you put the solder ball on kind of supports the solder ball, but also extends the length of that post, means that it can absorb more stress and put less stress on the solder ball. So it's these kinds of things that can be done at the packaging area to prevent solder joint fails. So in summary, because I'm at that point now, I think it's critically important. You know, packaging is critically important to the overall performance and reliability of electronic components. So that's kind of been from the beginnings of the industry. But it's evolved over time from these kind of very simple housings and simple packages to very complex multi-chip or multi-chiplet packages today. And packages can be highly customized for very specific applications. So the industry has become very good at designing for specific customer requirements. There's 3D and package stacking is certainly an important packaging trend. And some of those basic building blocks that I described today can be combined in many different kinds of ways to produce these very complex packages. And I think, as I stated a few slides back, you know, packaging today is probably as important as the wafer fabrication side. Without advanced packaging, you know, the industry really can't move forward. So thank you for your attention. I appreciate it.
Muchísimas gracias al señor Paul Hoffman. Señor Ramírez, ¿usted va a tener unas palabras? Pues le cedo la palabra en este momento y le cedo el micrófono para ello. Adelante.
Gracias.
Okay.
Pues muchas gracias, Paul, por tan interesante contenido. Yo creo que es muy importante, sobre todo el poder estar muy sensibilizados de lo que significa incursionar en esta industria de semiconductores, que en definitiva involucra, como bien nos ha explicado Paul, una serie de disciplinas. No solamente es electrónica como la conocemos, ¿verdad? De los chips, la electrónica que tiene que ver con transistores, elementos de RLC, etcétera, sino también involucra algunos aspectos muy importantes que tienen que ver, por ejemplo, con la ciencia de los materiales, con los sistemas de fabricación, con los sistemas que tengan que ver con fiabilidad. y todo lo que las propiedades mecánicas y térmicas que también Paul nos decía que son un aspecto crítico. Yo creo que para UNICARIBE y el gobierno de la República Dominicana, como ya se ha enfatizado, esta es una gran oportunidad para todos, digamos, los sectores que tengan que ver con la cadena de valor, y sobre todo nosotros que nos dedicamos a la formación del talento, pues nos compromete, ¿verdad?, de manera muy, muy especial el poder empujar con mucha fuerza el decreto presidencial del presidente Abinader, que definitivamente posiciona como política pública a la República Dominicana en un papel muy importante. Agradecemos a Paul, thank you very much for your talk, very interesting for all of us. Y yo quisiera, quizás, no sé si haya un tema de preguntas, comentarios, por ahí tenemos los micrófonos. Creo que lo pueden hacer en español, ¿sí? Creo que lo pueden hacer en español y ahí la traducción simultánea. Muy bien. Por allá tenemos una pregunta.
Hello, hi, how are you doing? Thank you for the presentation, it was very helpful. I have a couple of related questions. First of all, I was wondering, what do you see the space constraints projection into the future involved in data centers? So as basically as AI accelerator chips get developed and you need to pack more compute into basically the same space of a data center, will we see a similar trend that we saw from the move from PC to mobile, or do you see any other different dynamics with respect to that shift?
Yeah, so the major difference in the data center is thermal requirement. So if you looked at some of the pictures I had, right, there's a rack and there's processors and there's metal tubes. Those tubes are carrying liquid, carrying water from cold plates that sit on top of each thing. And unlike in a mobile phone, where we don't have the power dissipation, you can, shrink everything together and it's not so much of a problem. But in the data center, I think it's going to be thermal that limits the densification because you can't get the heat out. Yeah.
Understood. Thank you. One other question. In terms of the substrate materials question, in terms of the possible trends that might develop, how dependent are the other projections into the future for the industry, dependent upon the assumption that silicon will continue to be the standard bearer for the semiconductor industry and not another material will replace it?
Well, I think that is a good assumption, that it's going to be very difficult to replace silicon. I mean, you see other semiconductor materials certainly in other applications, silicon carbide or, gallium arsenide, whatever, but it's not going to be replacing silicon anytime soon. So I think silicon will be still for a long time, the major material.
Okay, thank you.
¿Alguna otra pregunta? Creo que por allá también. Sí, adelante.
Hi, my question is, what type of semiconductor we can start integrating, packaging, and assembling in Dominican Republic? And my second question is, because of the complexity of semiconductors increase each year, do you think AI is key to reduce the downtime of the development? Thank you.
Sure. So, I mean, that's an interesting question about, what kind of semiconductors could be adopted here in the Dominican Republic. And I would say not the most advanced, because that requires a lot of investment, a lot of knowledge. But there's a lot of semiconductor activity, both at the fab level and at the packaging level, that's not so advanced. And that would be a probably more logical place to start. So some of the less advanced stuff, yeah. Will AI be required? I don't know how important that will be. In industry, to my knowledge, like in the packaging industry, AI is not really a significant factor yet. We don't use it in our design processes or anything right now. We still rely on highly skilled people and using very sophisticated tools, but not AI driven at this time.
Saludo.
Adelante.
Yo quisiera preguntar sobre nosotros que somos profesores y tenemos la esperanza de poder tener equipos para fabricar aquí en República Dominicana, tener laboratorios en las universidades. ¿Qué usted recomendaría para el primer paso? Algo que sea realista, que podamos tener un laboratorio físico aquí en una universidad. Eso por un lado. Y por el otro, me siento tan mal por pagar $8, quejarme del precio de $8 por un micro, después todo lo que usted explicó es tan complejo que siento ahora que le estamos pagando hasta muy poco, en realidad, a los semiconductores. Gracias por las explicaciones, que no teníamos conocimiento específico.
Yeah, it's amazing how cheap some are for the complexity that goes into them. It's truly one of the aspects of the industry, the semiconductor industry, is because of that densification, the price has come down, right? And the functionality has increased. But back to your first question about, what kind of lab could you institute? And I will say that, like, if you look at U.S. universities, a lot of times they want to put in, they typically call them today, nano fabs or nanotechnology fabs. And in those kinds of labs, it's mainly semiconductor-based equipment, right? But it really depends on, I think, what kind of focus you want to have. There could be a whole focus on assembly and packaging. And the advantage of that is that the equipment is much less expensive. And, you could have a lab where you're experimenting and researching around different packaging constructs and different ways to build packages, or testing the performance of them, or any of those kinds of things. And it could be maybe a very effective way to start, and not as complex as putting in a nanotech fab.
Gracias. ¿Alguna otra? Por allá tenemos acá y acá.
Y por acá.
Si nos ayuda. Por acá también. Sí. Ramón.
Thank you so much, Mr. Hoffman, for your conference. Very, very good, to be honest. I have a question. In the IT side and information security side, we have leading practices. In this case, do we have any leading practice that we can take in order to ensure 2 points: quality and security of the semiconductors product, let me call it. That's all.
I'm not sure I understood your question exactly.
If you know about any ISO standard that we can apply in the semiconductors industry, because in the information security, IT, and all that side, we have a lot of ISO, but I don't know if in this field we have something like that.
Yeah, I can't remember the number, but there's an ISO standard that we all follow.
Okay.
But it's more around how you run the business. And it's a business practice of essentially how do you institute specifications, how do you make sure that specifications are working properly, how do you put a quality system in place. It's that kind of thing. So all fabs, all packaging houses adhere to those, have an independent auditor come and check that you're following those procedures. But we don't really have in the industry like a standard guidebook of how you do the processes, like the assembly process or something. There's nothing like that.
Okay. At least I know that there is an ISO available, so
Yeah.
I will look for it. Thank you.
Gracias. Por allá. Sí, adelante. Acá.
Good afternoon. Thank you very much, Mr. Hoffman, for your presentation and really for your time. My question is a bit of a follow-up question. You've mentioned so many different processes in the whole semiconductor assembly, testing, and packaging, and from that, there were a few let's say processes where there's already like an industry standard defined for them, such as like the IPC J standard 001 for soldering, and then like the AMS 2404 for electrolysis nickel plating processes. But what other like standards are there available for the semiconductor like industry,
Sure.
like for production?
Yeah, okay. So there's a series of standards that are specific, one part of this organization called JEDEC, JEDEC, that are specific to what the form of the package looks like. So there will be standardized packages like for a QFN 20 lead, certain thickness will be a standard, we call it package outline, and it will tell everything about that package, its thickness, its size, where the bond pads are located, their size. So for all standardized packages, those exist, and there's lots and lots of them. And then on more kind of like materials oriented, there's a organization called SEMI, and they have a number of specifications on semiconductor and packaging materials and how you test the materials and things like that. There's not really standards on package performance itself or design. Those are kind of left to the user.
Thank you. Sí, por allá había una. Sí.
Buenas. Sí, mi pregunta es, en términos de rendimiento eléctrico y térmico, ¿qué consideraciones deben tomarse en cuenta durante el proceso de encapsulado y empaquetado para garantizar la fiabilidad de los dispositivos?
So if it's a high-powered device, which I think you're maybe referring to, or an advanced process device, a lot of the concern is just getting the heat extracted from the device, the thermal power. So both at the semiconductor level and the package level, reliability is very dependent on temperature. So if the device operates at too high a temperature, it's not going to be very reliable. So the issue is mainly getting the heat efficiently out. So that relies on some of the things that I showed, having like a copper heat spreader in the package, a good thermal interface material between the chip and the heat spreader, maybe having thermal vias in the substrate, or having some part of the package substrate, if it's a lead frame package, exposed to the outside so it can be soldered to the circuit board, and then the heat can transfer into the circuit boards, things like that.
Ok. Otra pregunta. ¿Cómo afecta la elección de materiales en el proceso de encapsulado al rendimiento térmico del chip? Gracias.
Yeah, so it's actually, there's a complex kind of balance there. So a lot of the choice of that encapsulant material usually is a mold compound, usually highly filled with silicon dioxide particles, is so that the expansion rate of that material, it's not the same as silicon, but becomes closer to silicon. And it's hard to change that very much. So occasionally we look at putting other materials in, like maybe aluminum nitride as a filler in the mold compound, because that has a better thermal conductivity and might get heat out of the package more efficiently. But I would say, 95%, maybe 97% of the time, we're kind of just tweaking slightly that material that we already know performs pretty well, and not making very many changes to it.
Gracias. Por acá tenemos una pregunta.
Hi.
Hi.
Good. So my question is, what is your outlook on the legacy chips industry, and if you feel that might be a path to semiconductor for a country like this.
What kind of chips?
The legacy chips, like the
Oh,
metro
legacy
nodes.
chips. It's a potential path. You know, I know at Amcor that we would retire lines, you know, our older technology, and some of our customers will be, you know, where do we go now? And we didn't have an answer for them. As I said, you know, some of these older packages, they kind of never go away. And so there's always some kind of demand. So, I mean, that could be a strategy to be considered. You know, do you start with something that's kind of older technology, maybe a little lower technology, but still has demand?
Adelante. Adelante, adelante. Sí.
Buenas tardes. Tengo una pregunta. A nivel de producción, como estudiante de manufactura, ¿cuál debería ser nuestro enfoque o en qué deberíamos perseguir para desarrollarnos como profesional en un futuro en el área del ensamble de semiconductores?
That's a good question. So packaging is kind of maybe a little unique because a lot of different disciplines come into play. So you have to know something about materials and chemistry and bonding, and you don't have to as much, but if you want to be a good packaging engineer, it's good to know about the electrical side of it and thermal side of it. So I would say don't be too narrow focused. Maybe you want to have some breadth also. I mean, I think back to, even though my degree was in mechanical engineering, one of the classes I took was material science, and that was very valuable for me in my career to try and understand, you know, what was going on with the materials that we were working with. The other thing I would say is, you know, if you want to go into this profession, and what I never see taught at the university level is, in the profession we use a lot of experiments, but we use what we call design of experiments. We try to make a statistical basis so that we really understand and get an output that we can measure and know that the results are meaningful, rather than just kind of, you know, eyeballing the results and saying, oh, this is a better process. And we use that, we rely on that, but I never see that taught anywhere.
Muchas gracias.
Hi everyone. Thank you, Mr. Paul, for the presentation. I have a question. What software CAD is used for thermal analysis and stress analysis in packaging semiconductor?
Thermal and what was the other analysis?
And thermal analysis and stress analysis.
Yeah. So ANSYS is a popular one. Yeah.
Julio.
Hola, muchas gracias por la presentación. Tengo una pregunta. Si una empresa como Amcor quisiera relocalizarse en República Dominicana, ¿cuál sería el proceso primordial que traería para nosotros y cuál sería su demanda de personal? ¿Cuántas personas cree que necesitarían?
Yeah. If you've ever seen pictures of semiconductor fabs, they're very automated. And I'll talk about packaging in a second. But in a semiconductor fab, you may see rows of equipment, and you see overhead vehicles or robotic vehicles transporting wafers from process station to process station. Very few people in those factories. But that's not like a packaging and assembly factory. In a packaging and assembly factory, you generally have a lot more people than you would in a wafer fab. So, you know, if part of the desire is to have a higher number of local employees, then the packaging, you know, factory is a lot more friendly than a semiconductor fab. So that's one thing I would say. Yeah, it's difficult. It's difficult to I guess, try and summarize all the factors that a company like Amcor would put into their decision-making process of where their next factory is going to be. A lot of it is based on the infrastructure in the country. So I can tell you that we were very frustrated when we had factories in the Philippines when they first started out, because the simple thing like the electrical infrastructure, the power would go out and we'd have to shut down our factory, or we'd have to rely on our own backup generators for long periods of time, and that was very frustrating. So those kinds of things. What's the infrastructure like? But not just like physical infrastructure, not just like electricity or water, but also the human resource, right? And that's critical. So and we would look at things like what is the unemployment rate like? What is the skill level of people? What do the university systems look like? Can we find graduates that we can put into engineering roles? Because, a factory has all levels of people, right? You don't just have operators on the line, but you have managers, you have engineers, et cetera. And you need skilled people, and you need people also that are more maybe good with operating equipment. So it's a whole range of things that we look at. And the other thing that's maybe harder to quantify is I think the industry is a little bit driven by, where is your customer base and what are they doing? So Amcor's, last factory they installed was in Vietnam. And one of the major reasons they did that was because Intel was installing, operations in Vietnam. And then other people started going to Vietnam. And I think Amcor was like, well, we want to be part of that, new site and new location that's developing, and we don't want to miss. Yeah.
Sí.
¿Por acá?
Por aquí.
Sí. Acá. Muy bien.
Sí, gracias. Bueno, gracias por compartirnos en tan poco tiempo tantos años de desarrollo e investigación que se ha llevado a cabo para la industria de los semiconductores. Entonces, quiero, en la misma línea que usted comentaba, saber los principales perfiles que son necesarios en una primera etapa para nuestro país en la industria de semiconductores. ¿Cuáles podrían ser esas principales profesiones que necesitaría esta industria?
Yeah. Well, in packaging specifically, it's some of those things I've talked about. So material science, chemistry, metallurgy even. But oftentimes just general good engineering skills, because those are transferable, right? I mean, a lot of, whether it's in a semiconductor fab or in a packaging factory, a lot of what you learn is not taught in school. It's that you've learned a methodology of engineering and science, and you can apply that, right? Because nobody's going to teach you in school, what makes a good flip chip joint. And that's never going to happen. So it's kind of about the basics in many respects. I will say, and maybe this is a very prejudiced of me, but I will say that I've seen other countries been maybe very successful in kickstarting their English language studies at low grades as part of their overall country strategy. So I remember visiting Malaysia a number of years back and talking to somebody there, and I was commenting, your English is very good, and they said, well, it's been a government policy to have English in our schools, mandatory, for many years now. And I said, well, how much English do you learn? And he's like, I think it was like 2 hours a day or something. I said, that's more than my kids take in English. It's crazy, so maybe it's changing, but I think still, in the business world, English is kind of the common language worldwide, so, and maybe the technical language worldwide, so that may be a factor too.
Gracias.
Buenas tardes. Muchísimas gracias por esta interesante formación. Muchas felicidades porque realmente han sido largos años de estudio, de trabajo y de experiencia que ha compartido con nosotros en esta tarde. Mi pregunta es en cuanto al grafeno. En el área de ciencias de los materiales se ha constatado que el grafeno es uno de los materiales con una alta conductividad térmica y entonces con todo el tema de los semiconductores, ¿cuál es el estado o la perspectiva en cuanto al grafeno para que sea utilizado como un, digamos, sustrato que podría garantizar los mecanismos de enfriamiento para estos equipos? Muchas gracias.
Sure. So I guess, graphene, yes, extremely high thermal conductivity. Graphene itself, the strict definition is it's one atom layer thick. So by itself, it's not going to be a very good conductor. But we call it graphenite, but, like particles of graphene impregnated in other materials, that might be, I think, more interesting way to use the thermal conductivity. In terms of application in the circuit itself, people have looked at and kind of concluded that graphene is never going to make a transistor. So it's not going to be used, in place of silicon in a logic device, let's say. But it does have some very interesting possibilities for sensors. So in one of the companies I worked at, we were actually using graphene as a sensor for looking at DNA recombination. So it's a very sensitive material.
Hi, Paul. First of all, thank you for the talk that you've given. For you, what would be the perfect profile or technical abilities of a packaging engineer today?
Well, so you don't have one overall profile. There's not like one perfect profile because, like in my group that I had at Amcor, it was kind of dependent on the function that you were needed to perform. So if I needed a guy to do electrical simulation, his profile was quite different from a guy that was going to do package development and needed to know about materials and assembly processes. So I don't think there's one profile. There's maybe 4 or 5 profiles depending on kind of what area you want to specialize in, whether it's an electrical simulation guy, and design guy, thermal person maybe different, materials guy, and then assembly, let's call him assembly packaging engineer. And that guy is probably the one that has the broadest range of education. So a little material science, or maybe a lot of material science, maybe a little chemistry, maybe a lot of just strong general science and general engineering. Again, not so much for the specific knowledge, but for the how do you approach a problem and how do you problem solve and things like that.
Gracias. Por acá.
Muy buenas tardes. Tengo 2 preguntas. La primera es respecto a la maquinaria, a las herramientas que se utilizan para realizar las interconexiones de los circuitos integrados. Con respecto a esto, la maquinaria que se utiliza normalmente desarrollan un solo tipo o diferentes tipos de interconexiones. Y la segunda pregunta es, ¿puede un fabricante generar el mismo part number, o sea, el mismo integrado con diferentes técnicas de interconexión?
Okay. Okay. It wasn't working at the start.
Okay. Bien. La primera pregunta era con respecto a las maquinarias o las herramientas para realizar las interconexiones de los integrados. La misma maquinaria se podría utilizar para diferentes interconexiones. Por ejemplo, usted habló del wire bonding y de otros tipos de interconexiones. ¿Podría una sola maquinaria desarrollar diferentes tipos de conexiones? Y si un fabricante puede el mismo microchip desarrollarlo con diferentes técnicas también.
Yeah. So there's different equipment for different processes and different materials, but the type of, I talked about, sputtering equipment and plating equipment. The same type of equipment could be used either at the wafer fab level or it could be used at the package level. And that could be used for creating, for instance, copper interconnects. But if you're talking about some of the interconnects at the packaging level are very specific, right? So a wire bond, that kind of wire that went from point A to point B, that's a very specific machine. It doesn't really have any other purpose. So it really kind of depends on what do you mean by interconnect and what do you want to use it for. But as I said, there's kind of a blurring of the lines between wafer fab and packaging. So essentially all the equipment that we would use for a wafer level package could also be used in a wafer fab for interconnection.
Muy bien, gracias. Por acá, al fondo, tenemos una pregunta también. ¿Por allá? Ya no hay preguntas. Sí hay.
Hello? Hello, hi. I have a couple more questions. I wanted to follow up on an earlier question regarding the ability of the Dominican Republic to onshore some of the ATP phase in the semiconductor supply chain. And specifically, I was wondering if you could be more precise in terms of precisely whether or not it's just traditional packaging that you think we should stick to, or do you think that advanced packaging is within reason for us? Like, can you speak a little bit more about that? And then the second question I want to also ask is, you mentioned how fabs tend to be highly automated. Do you see that as the future also for advanced packaging or just traditional packaging? I ask because if that is the future, then perhaps it might not be the most wise thing to do to try to onshore the industry and then not have any of the people benefit from it because it'll all be robots.
Yeah. Let me answer your last question first. I don't think assembly and test will become as automated as wafer fab anytime soon. I mean, it's expensive, very expensive to put that kind of automation in. So it's in these, $30 billion fabs that's being done. But, packaging probably couldn't support that kind of cost. So I don't think that's going to happen anytime soon. I mean, I'm sure there'll be some additional automation over time, but I don't think it'll take over the factory. To your first question about Dominican Republic, I'm not an expert in the Dominican Republic, so it's very hard for me to say. I don't really know well, what the education level might be here, the skill sets, what other kind of typical industries are here in the country that might, kind of mesh with doing packaging. But what I can say is that it doesn't really matter if it's the Dominican Republic or the United States or, Korea. If you want to put in advanced packaging capability, you're talking about very high tech. You're talking about expensive equipment. You're talking about very highly trained engineers, and so expensive engineers, and it's not easy, right? And it's not easy not only because it may be difficult to put in and get that kind of factory running, but you also have to convince the customers that are going to use that factory that you're capable of doing that. I think it would be much easier to say, you know what, we're not doing the last generation, we're doing the previous generation technology. And your customers would probably feel more confident that you would be able to do that kind of packaging. Yeah.
Okay, gracias. Creo que es
Yes.
allá. Sí, adelante.
Okay. Thank you so much again for all the knowledge you've been sharing with us. I have a quick question, and it is, I run an entrepreneurship center for a national university. So what kind of initiatives or ideas we may implement in our Center of Entrepreneurship to drive students and encourage them to build the startups based on this industry? Thank you.
Yeah. So the startups that I have seen in this industry are pretty specialized and they're pretty leading edge. So very high tech, very sophisticated kind of guys that are thinking 3 or 5 years down the road, and it's typically people that already have experience in the industry. It's not new guys, because they've seen, you know, kind of what's worked in the past, and they're trying to project to the future. So that's a really difficult one, I think. How do you instill that in somebody if you don't have a previous basis, you know, locally where you can find that kind of talent? I'm not sure how you do that.
Okay.
I mean, I guess to further answer your question, it's one thing to say I want to start a packaging factory, let's say, in the Dominican Republic. That's one thing, right? But to me, that's not entrepreneurship, right? That's kind of, I guess, in some senses, it could be entrepreneurship, but it's really based on an existing model, right? You're not really forging new ground versus, you know, the startups that are in packaging. It's like we're throwing away most of that old technology, and we're forging some new technology, and it may or may not get adopted by the industry, but that's kind of the space that at least the packaging startups in the U.S. are operating in.
Okay. I have a question, Paul.
Yeah.
Imagine you are the president of the Dominican Republic. Okay? What is the main action to promote the semiconductor industry?
You know, I think for me, it would be education, actually. I think you can't build a technical industry unless you have technical people. And you can't have technical people if you don't have the education system to support it. So I don't know, maybe that's kind of a long-term thing, but I think that's a critical basis.
Thank you. Thank you very much, Paul, for your talk.
Thank you.
Aplauso, un gran aplauso para nuestro instructor Paul Hoffman. E igualmente para quien ha estado en el escenario, el señor Ramírez, acompañándonos en este momento de preguntas y respuestas. Y bueno, yo creo que ha sido definitivamente una jornada muy provechosa y hemos notado el interés de todos los presentes con esa avalancha de preguntas, además, que se le hizo al señor Hoffman en este día. Todos ustedes estarán recibiendo su certificación por la vía digital. Los certificados van a estar colocados acá para que ustedes puedan verlos en este momento. Ahí tenemos a las instituciones participantes también. Así va a quedar el certificado de ustedes. Y las empresas, las instituciones, disculpen, participantes son UNAPEC, UTESA, ITLA, la UAS, UNADE, OIM, ITSC, UPIT, UCE, INTEC, Pucamaima y UNICARIBE. Definitivamente ha sido una jornada maravillosa. Queremos recordarles que este programa de formación es el primero que tiene lugar en la República Dominicana. Y tal como decía el señor Hoffman, el paso fundamental para que comencemos por este camino es la educación. Y eso es lo que estamos haciendo hoy. Este es el primer paso de tantos que nos tocará dar para que podamos llegar a insertarnos realmente en lo que es este campo de los semiconductores, un campo tan tan, pero tan significativo dentro de lo que es la tecnología moderna y así poder también insertarnos en la competencia global y República Dominicana pueda participar en ello. Muchísimas gracias al señor Paul Hoffman por acompañarnos, nuestro instructor estrella que nos ha premiado con este día compartiendo sus conocimientos. Ese es el QR que ustedes deben, por favor, tomar para que puedan registrarse. Tienen que colocar su nombre completo correctamente para que a nombre, precisamente el nombre que ustedes coloquen allí, será el que saldrá en su certificación. Colocar su correo electrónico, fíjense bien que esté escrito de manera correcta porque a ese correo electrónico en unos minutos será que se les hará llegar el certificado virtual. Cerramos este programa de formación entonces agradeciéndole a cada uno de ustedes por su presencia en este día completo. Esperamos que nos volvamos a encontrar nuevamente y por supuesto invitarles a que sigan compartiendo de este entusiasmo, de todas las ideas que ustedes puedan tener en ese espacio en el que queremos invitarles a un nuevo coffee break. Tengan feliz resto del día y gracias a todos por su participación. Un nuevo aplauso para Paul Hoffman. Gracias a todos. Buen día.